Hello, scholars. Welcome. Professor Henkle here. Today, we are going to discuss ocean circulation. This is a big topic. This encompasses all the movement of the water throughout the entire Earth's oceans, and there's a lot of really cool phenomenon that are associated with this. So, we will start simple and we will build more and more layers, more and more complex as we go, tying it all together into a nice little bow at the end. Exciting stuff today, so I'm really, really happy to share all of the important features of ocean circulation. So, what are they? Well, we will identify major ocean surface currents of the world, gyres, subtropical gyres. We'll look at the most famous and well-studied of all ocean currents, the Gulf Stream, how it creates warm rings and cold rings. We'll look at the development consequences of the Ekman spiral, Ekman transport, talk about geostrophic flow, western intensification, and then upwelling and downwelling, and touch upon primary productivity. It's all linked. It's all in there together, but this is kind of the supporting features for the marine life environment. We'll discuss ENSO, which is El Nino, La Nina, how they form, why they happen, some of their effects. Talk about Langmuir circulation, get into Thermohaline Circulation. This is the movement of Earth's ocean water on the surface and deep below throughout the entire planet. Talk about temperature salinity diagrams, and then finally round it out how deep water circulates throughout the world's oceans. We'll touch upon energy and climate at the end also. Okay, are you ready? Pencils out? Brains on? Perfect. Okay, let's go. So, very simply, there is water in the ocean. The ocean is made of water. It's salty, 3.5% or 35 parts per thousand, if those are ringing any bells. And this water moves. Now, we can categorize the movement of water in two places, on the surface and deep. So on the surface, underneath the surface. If we remember from physical oceanography, there are features like temperature, salinity, density, where a lot's happening in the mixed layer, and then you have this abrupt change, thermocline, haline, pycnocline, and then below that, which is 200 to 1,000 meters roughly, stability starts to happen. It levels off. And so above these areas of rapid change, above the thermocline, we have surface currents, about 10% of the ocean water, and below we have deep currents, the other 90%. And we can observe movement of surface currents through fortunate accidents, serendipity. For instance, in 1992, when the Everlaurel storage tanker ship was traveling from Indonesia to Tacoma, Washington, dropped a bunch of containers carrying plastic floating toys. Well, they floated, and they transported all around the oceans on ocean currents. And these toys were discovered throughout different periods of time. The accident happened in 1992. About 4 years later, they started to wash up in Tacoma. Then roughly 3 years later, it varies, right? 3 years later, started to make it through the strait between Russia and Alaska, circled around the Arctic, started to appear here about a decade later in the North Atlantic Ocean, ending up on the east coast of the United States in the Atlantic Ocean, and then all the way 15 years later, some of these toys were discovered in Northern Europe. So it was kind of like a science experiment that was unplanned, where if we place devices, in this case toys, in the ocean, where do they go? Let's track their progress and see how ocean currents move. So, surface currents are wind-driven, primarily horizontal. Deep currents are vertical and horizontal. This is caused by physical oceanography features. Temperature and salinity, which change the density, and as we are familiar with, less dense like hot air floats, more dense like cool air sinks, less dense water rises to the surface, more dense water sinks down to the bottom of the oceans. So how do we measure it? Excuse me. Two ways: direct measurements and indirect measurements. So we've talked about this, getting our bearings and trying to understand how to actually collect measurements. So drift meters, floating devices in the ocean that collect data through time, is a good way to observe the movement of ocean surface currents. There's also Argo floats that dive deep down. Whole slide on that in a second. Indirect measurements, looking at differences in pressure using radar, altimeters, and Doppler flow meters to get a less accurate but greater coverage understanding. Indirect measurements come from satellite ocean dynamic topography, which topography is on Earth. It's the elevation of the surface. So ocean topography is the elevation of the ocean. And so it makes sense. It rains in the mountains, the rain collects into rivers, travels downslope due to the force of gravity. It gets to the ocean, no more gravity. Well, that's not the full story. The ocean has areas that are higher and lower. It's subtle, but we can record the elevations on the surface of the ocean. And just like water flows from high to low, same thing happens in the oceans, and we can start to gain an understanding of the direction oceans are flowing from these dynamic topographic measurements through the Topex Poseidon radar altimeter, showing variations of sea level height. Really cool stuff. Deep currents use these free drifting profile floats called Argo, and they work like this. This is a direct measurement, by the way. Put an Argo in the ocean, it's recording where it's going, and then it dives down deep into the ocean, and then it comes back up, recording its location all along the way. And given those measurements, we can start to get an idea of what's happening underneath the surface of the Earth. There's also putting plumes of different materials, different chemicals, and then tracking the movement of these chemical plumes. They're called tracers because we're tracing their movement in the oceans. And excuse me, developing characteristic temperature and salinity profiles, which help us to gain an overall view of ocean circulation patterns. Surface currents occur within and above the picnic line. About 10% of all the ocean water, as mentioned, happen because of friction between the wind and the ocean surface. The atmosphere and the hydrosphere interacting together, and in this case, wind, due to pressure gradients in the air, drags along the surface of the Earth, and the friction between the wind on top of surface ocean waters causes surface currents to work. These wind currents have general patterns, circulation patterns, as convection cells. There's 3 of them. And oceanographic circulation generally follows wind circulation because of the direct relationship, one causing the other. Surface currents are affected by these big blocks of rock that are scattered all throughout the Earth, called continents, and also gravity, friction, and the Coriolis effect. Thank you to the spinning of the Earth and this apparent deflection to the right, northern hemisphere, and to the left, southern hemisphere. That interaction of continents, Coriolis effect, friction, wind, creates what are called gyres. Gyres are circular patterns of movement within the oceans. There are 5 subtropical gyres. There's a lot of gyres, smaller ones, but big ones centered around the tropics, right around 30 degrees latitude, have bounding currents, equatorial currents, western boundary, northern boundary, eastern boundary. In the southern hemisphere, it would be a southern boundary. And these are really important to understand how oceans circulate, how surface currents works. Well, they work in these big circular motions. So if we look at a map of the world and the world's oceans, maybe a brief review. So there's 4, maybe 5 asterisk oceans in the world. The Pacific, the Atlantic, the Indian, the Arctic, and, this is the asterisk, the Southern, which is kind of the collection of the bottom of the Pacific, Atlantic, and Indian, but it can be pulled apart, and part of the reason is because you have this circumnavigation, this circumcirculation above Antarctica. So here we can see the gyres centered around South Pacific, North Pacific, South Atlantic, North Atlantic, Indian. These are the 5 major subtropical gyres, and they're connected through thermohaline circulation. So this is where you could almost say there's one ocean on our Earth, but for our understanding, we like to make it more complex. And how do we do that? We divide them and understand individually to aid in our understanding. Please be sure to watch this video. It's really good. Now, the Gulf Stream is a northern boundary current for the North Atlantic subtropical gyre. It's really famous. People have been observing it for a long time, specifically in maritime navigation, all the way back to Benjamin Franklin creating a map that actually had the Gulf Stream on it. And what was noticed here was when traveling from Europe to America and back, there was a channel of warmer water traveling from the direction of America to Europe. And if you're going America to Europe, you want to be in that channel. And if you're going the opposite direction, you want to be out of that channel so that your travel time is decreased. Now, sailors started to maybe not understand the ocean circulation properties of subtropical gyres, but in real time, hey, faster here in warm water going this direction, faster out of warm water going the other direction. And so use thermometers in the water to locate where this current was, this current being the Gulf Stream. So it's really well studied. It moves along here in a temperature map of sea surface. It originates down here in the Gulf of Mexico, moves northward along the east coast, and then travels all the way across the North Atlantic Ocean. Creating what's within this is the Sargasso Sea, which has a unique biology of marine kelp. Really awesome. So this is our first little discussion, kind of a hint, foreshadowing of the future, that physical properties of the ocean have unique characteristics and support unique biological populations. And in fact, it's because of circulation patterns, upwelling and downwelling, more of that to come, that we have areas of very high productivity and areas of very low productivity. And we'll know all about that when we talk about primary productivity. So the Gulf Stream, this is really cool. It meanders like a river meanders. Now, the reasons are different. Rivers meander to find a balance between the amount of water and sediment that's being input into the system. The Gulf Stream meanders because of the relative proportions of cold water above it and warm water below it. So you could think, here we can see the Gulf Stream, warmer water below. here's a cold core ring, here's another cold core ring, here's a warm core ring, here's another warm core ring. And basically, if we go along and we see, let me find my handy dandy pointer here. We see the Gulf Stream traveling along, and then it starts to meander. Well, a meander bends into the cold water filled with warm water. It also bends into the warm water filled with cold water. And then the bend starts to cut off, trapping a pocket of warm water here and a pocket of cold water here. Those pockets can migrate off and again support unique biology. Species specially adapted to survive and to reproduce off of these pockets. Fast forward to marine fisheries, which we'll talk about. Fisheries have begun to understand where these are, and if you're a fisherman wondering where the best place to go fishing is, understanding how the Gulf Stream works and understanding where you may find these warm core rings is really important for helping to find the resource that you are seeking. Really great video on the Gulf Stream, so please be sure to check this one out. Also, if we go down the list of really big topics, our first big topic here is gyres. The next big topic is the Gulf Stream. Ocean circulation, complex, breaking it down into its individual pieces of the system, a system being a set of components that interact together to form a whole. What we'll record here are components of ocean circulation. Ocean circulation is a component of the ocean system. Oceans are a component of the hydrosphere. Hydrosphere is a part of the Earth system. So it's all about layers, the scope for how we're trying to understand a certain process or phenomenon from the microscopic all the way to the macroscopic. Okay, so it would seem that wind blows and it drags the water along with it, and end of story, the end, goodbye. Well, actually, it's a lot more interesting than that. So there was an observation where sailors were noticing the wind was blowing this way. I'll point directly to you. The wind is blowing this way, but ice is floating this way, 20 to 40 degrees. What the heck is going on? Why, if the wind blows this way, the movement is that way? Well, a researcher came along, Ekman, and started to observe and model and understand, and what he found were these two phenomenon, Ekman transport and Ekman spiral. So if we're thinking about the surface water, there's the very top, and then there's layers down. Well, as wind blows across the top, that energy is being transitioned down, and as it moves down, because of the Coriolis effect, water one layer beneath is turned, a layer beneath is turned, turn, even to where water at some depth goes the opposite direction. That creates a net 90-degree movement from the direction of the wind. Really awesome. It's 90 degrees to the right in the northern hemisphere, 90 degrees to the left in the southern hemisphere, again because of the Coriolis effect. Now, all the different directions of movement of the water column going down, this is Ekman's spiral, and the net movement to the right, northern hemisphere, to the left, southern hemisphere, is known as Ekman transport. Great. Really cool topic. Awesome video. Imagine that. Please, please, please pause the video right now. Watch this video. It is pause the pause the lecture, the one that we're in, and then watch this video. It will help. It'll make a lot of sense. Okay. One moment. Nice to have water within arm's reach. Okay. I apologize for that. I got a little frog in my throat. Just got to get that frog out and I will be good to go. Okay, so geostrophic currents. This is really, really cool. So if we have an understanding of Ekman transports and the Coriolis effect, well, the two of these interact together to create little bulges. They're a rotational flow, as we can see here, in an ocean basin, where Ekman transport is moving water in one direction, creating a bulge, but underneath the influence of gravity, the water moves back out. Now, these rotational flow, due to the interaction of Ekman transport and gravity, is what we call geostrophic currents. Let's go here. Excellent. Okay. Moving on, next topic. I know, big topics. This is a nice introduction to all of them. Western intensification. Same in the southern hemisphere as it is in the northern hemisphere. This is because every night I go to bed and every morning the sun comes up again. Why does that happen? Well, because the Earth rotates on an axis once every 24 hours. It also orbits around the sun once every 365 days. The two of those give us seasons. Really, really cool stuff. Love that topic. But because the Earth is rotating, as it rotates on the east side of these circular patterns of movement, the currents get spread out. On the west side, the currents get squeezed together. That's a good way to think about it. And so what this does, right, is it makes the currents more intense on the western side, less intense on the eastern side. And the name of this phenomenon we give western intensification. Cool. Upwelling and downwelling. So it's not all horizontal. There's a little bit of up. There's a little bit of down. Now, this can help to support the interaction of surface currents and deep currents. Surface currents become deep currents by downwelling, and deep currents become surface currents by upwelling. Important because there's a lot of nutrients that settle down to the bottom of the ocean that primary producers, marine phytoplankton, need to reproduce. Well, if it's all at the bottom, how does it get to the top? Well, through the process of upwelling, and it happens in a few different ways. So definitions here. Upwelling, vertical movement of cold nutrient-rich waters to the surface, areas of high biological productivity. Downwelling, vertical movement of surface water downward in the water column. Water piles up, low biological productivity. Here's the equator. We have the north equatorial current, Ekman transports, causing water to move 90 degrees to the right. In the northern, 90 degrees to the left. In the southern, this is an area of divergence. See these arrows diverging away from each other. Okay. Because of the divergence, what's got to fill this is water from underneath. This also happens along coastlines, and these figures give us a little bit more of a visual kind of understanding. So wind is blowing from the top to the bottom. We're going to say, if this is the west coast of the northern hemisphere, hey, look, here's California. And the wind is blowing from north to south. The direction of movement is 90 degrees. So you see these arrows, 90 degrees from this arrow to the right, chunk, chunk. Well, if the water's moving out here, then water from underneath needs to come up to fill it, creating upwelling. Now, same place, but let's switch the wind direction. 90 degrees to this way, to the right in the northern hemisphere would be towards the ocean, causing it to move down underneath the surface in downwelling. Again, lack of marine life in downwelling, abundant marine life in upwelling, because upwelling provides nutrients and primary productivity. The food web in oceans needs two things: nutrients and sunlight. That's why it happens in the top, because that's where the light is, and where upwelling occurs, that's where nutrients are. Again, lots of that to come. Okay, let's put it on the board as another big topic of discussion. Great. So these are happening. Subtropical gyres, surface currents like the Gulf Stream, Ekman transport, geostrophic currents, western intensification, upwelling and downwelling, and they create unique properties for each of our different oceans. So let's go way down to the South Pole, the Antarctic continent, and around it we have Antarctic circulation. Now there's a couple things going on here. There's Antarctic divergence and Antarctic convergence. Where water converges, it downwells, lack of marine life. And where water diverges, water comes up from underneath, that's upwelling. Awesome, great. And this happens because of two specific currents: the Circumpolar Current, also known as the west wind drift, and the east wind drift. Now, what these do is they create divergence in certain areas and convergence in others, creating this band right here along the Southern Ocean that wraps around 3D Earth, 2D model, 2D map, that wraps around, creating an area of high productivity, but only for half the year. Why is that? Oh, because at the poles they experience extreme seasonality, 6 months of light, 6 months of dark, and it's in those 6 months of light where photosynthesis can occur. Pacific, north and south, made up of specific currents. In the northern Pacific, we have the North Equatorial, Kuroshio, the North Pacific, the California Current. Notice there's another Alaska current up here forming a smaller gyre. We've got another current up here. Down into the South Pacific Subtropical Gyre, we've got the South Equatorial, the East Australian, the West Wind Drift, the Antarctic, and the, the Peru Current. Now, what's important to know here? What jumps out when we look at this figure? Warm currents and cold currents. So, it's cold in the poles and it's hot at the equator. That makes sense. Our brains can understand that. So we have the movement of heat. Oceans distribute heat across the globe, and they do so via ocean currents along the surface, and they happen in a systematic way through these subtropical gyres. So, west coast of North America receives colder water from the North Pacific. If we were to spin the globe, it would be the eastern side of North America. In fact, let's just spin the globe right here. The eastern side of North America for Atlantic Ocean circulation gets water from the equator. So if you go swimming in Washington or you go swimming in Florida, the temperature of ocean water is going to be very different. because the water in Washington is coming from Alaska, and the water in Florida is coming from the equator. Cool. Okay, so here we can see subtropical gyre. I don't think I emphasized this, but they spin to the right in the northern hemisphere. The circular motion is to the right, and the circular motion is to the left. Again, this is because the Earth spins, it rotates on an axis, creating the Coriolis effect. Indian Ocean circulation, unique phenomenon. So there's a seasonal reversal of wind direction over the northern Indian Ocean. This is known as monsoons. This happens because of the differential heating of land and sea and the fact that there are seasons. Tilt of an axis pointed 23.5 degrees to the North Star. Orbit of the sun or of the Earth around the sun, heliocentric, not geocentric, creating a northeast monsoon winter, a southwest monsoon summer, thereby affecting where the location of the subtropical gyre is, and the importance, or one reason that we could say this is important, is because it creates seasonality for primary productivity. Here we can see the summer monsoon, high productivity, which means that what must be occurring? Upwelling or downwelling? Upwelling, excellent, very good. In the winter, we have the opposite happening. Downwelling is occurring, low biological activity. Let's talk about something else that's pretty fun. El Nino. So I wonder what comes to your mind when you hear the word El Nino. Maybe you have a memory of big storms, of big floods, of some kind of weather that was occurring. Well, it is a weather pattern, but it's caused because of what's going on. Well, not necessarily just the ocean, but it's ocean circulation patterns. It's the ocean-atmosphere interaction, the air-sea interaction. So, under normal conditions, along the equator in the Pacific Ocean, we have what is called a Walker circulation cell, where the currents go from east to west, western intensification happens, there is a location of the thermocline at depth, and a pool of hot water that creates a low pressure system. Low pressure moves to high pressure, and giving us normal conditions, right? And so normal comes from climate. Climate is an average of weather conditions over a period of time. Weather conditions are what's happening right now. It's raining outside. That would be weather. In the month of December, on average, it rains 10 inches. Oh, that's climate. So if in the month of December it rains 50 inches, that's an above average rainfall. That's divergence from the norm, right? And so we establish baselines based on what happens through time on average, and then we have perturbations from the norm. So this is a natural process, Walker circulation. El Nino happens, the winds are not as strong, so the warm pool was here, now actually travels further to the east, taking the low pressure cell with it. The thermocline is a little bit deeper in the eastern Pacific, causing downwelling. This upsets fishermen because normally highly productive waters no longer have the same amount of fish that are available for fishing, and it causes big storms and big storms and flooding on these Western American coastlines, North America, South America. I'm talking about continents here. Gotcha. So El Nino happens because of changes in the wind that affect where the location of warm water is along these equatorial currents. There's a great video, Understanding ENSO. Please stop here. Go watch this. Welcome back. How was that? Awesome, right? Please do it if you haven't yet. Okay. La Nina is the opposite. Here now we can see water is pushing that warm water spot further to the west. There's stronger trade winds. The thermocline is much shallower. The seawater gets colder. We've got upwelling occurring, higher biological productivity, creating conditions on the western coasts of the Americas that are drier. Please check out the La Nina video. Huge topic, El Nino, La Nina. Really cool stuff here. So, El Nino is hard to predict. We don't even completely understand it because we're still learning and it's so irregular. It happens every 2 to 10 years. These phases can last 12 to 18 months. It's possible that ENSO events on their irregular pattern are part of a larger cycle, the Pacific Decadal Oscillation, the PDO, that could be long-term natural climate variability on the order of 20 to 30 years. So we can see departures from the norm, standardized, when we have oscillations around creating El Niños and La Niñas. The effects are felt globally. We talk about what's happening here close to home, maybe because it's more tangible. El Nino in California means flooding, big storms. In other places, it means drought, fire. It can create tropical storms. It can damage coral reefs. Marine life can be impacted. Severe flooding can occur. Now notice this is all within about 40 degrees on either side. The effects, right? This is an equatorial current phenomenon that's happening, and so the effects are felt within the range of these subtropical gyres. Again, we're connecting different concepts. These all work together to produce what we see on Earth. So, I remember 1997, I was in 7th grade, going to Hoover Middle School in Merced, California, and school got canceled because it had been raining, and then it just started to rain and rain and rain. So much so, wow, okay, so school's canceled. The street that the school was on, I lived in a 5-minute walk, was completely flooded. I had to hike across up to my knees. It was real wild. Fortunately, my house didn't flood, but a friend of mine's was flooding. So I went over to his house, helped him and his parents throw sand in a bunch of bags, block the garage because his whole block had become really flooded, and it was very memorable. That same storm flooded the entire Yosemite Valley. There's a really cool sign that shows you, and this is like, oh, look, hey, look how big the flooding was. It's on this big tree on January 2nd, 1997. So this wasn't the only time. We've had big ENSO events in the early 80s, the late 90s, the mid-teens. When the next one will occur, hard to predict, hard to know. So I love this figure here, right? La Nina, normal Walker circulation, El Nino. The colors are sea surface temperatures. In here we can see normal temperatures. There's a shift to the left. We've got the western intensification. La Nina, it's a big shift to the west. And El Nino, these warm waters shift to the right. If we bring warm, moist water to the west coast of the Americas, it causes more rain. And so we see that. And it's not specifically it rains everywhere. That's a overgeneralization. But let me say that in the dynamism of these shifting waters, a whole plethora of different weather effects can be felt on these coastal and land areas. So scientists are working hard. The TOGA program, Tropical Ocean Global Atmosphere, monitors the currents through a system of buoys. We've got satellites. The Tropical Atmosphere and Ocean Project monitors also. We don't quite fully understand ENSO, but this could be your life mission. You could, if you think this is so cool, you could dedicate your life to learning and studying and understanding El Nino, and it would help a lot of people prepare for some of the effects that can be caused from these different types of El Nino and La Nina events. So, big topic, El Nino, La Nina. This is like a special mention, honorable mention of ocean circulation. Langmuir circulation. So it's smaller phenomenon, but this is basically happening when you get alternating regions of convergence and divergence, which looks like lines in an ocean area, and you get upwelling and downwelling occurring. Very, very distinct phenomena. Really cool. Honorable mention. Thank you, Langmuir. Okay. It's a lot on the surface. I touched on the deep ocean a little bit, but let's really talk about it now. So there's water in the ocean, and the water moves on the surface currents, and below the ocean, deep water currents. And we call there are these huge masses of water. They're actually called water masses. Water mass is a volume of seawater with a very distinct temperature salinity profile. Now, this is important because there's a couple places where there's deep water formation. For the Atlantic, it's up here near the Greenland Sea, and then also down here in the Weddell Sea. What do these two places have in common? The water is very cold in the poles. So these are areas where surface water gets colder and the salinity increases. That increases density. More dense water sinks down to the bottom. And this is the connectivity of surface and deep water masses. We can understand these different deep water masses on a TS diagram, temperature salinity, because they have very specific characteristics for what the salinity here, average ocean salinity is 35 parts per thousand, or 3.5%. It varies throughout the oceans, and also the temperature varies by latitude and with depth. Remember, average ocean temperature is around 4 degrees, but again, that varies too. Deep water can be really, really cold. So, ocean circulation, deep water masses, surface water currents connects in the global conveyor belt of ocean water that is called Thermohaline circulation. Let's break it down. Thermo, heat. Haline, salt. Because of temperature and salinity, we have differences in density that cause certain areas. Here's deep water formation in the Greenland Sea, deep water formation in the Weddell Sea, and movement, red is surface, blue is deep, of ocean waters distributed around the entire globe. Now, this is really important for moderating global climate, for transporting heat, for moving nutrients, supporting marine life. The connection of the oceans is one of the unique features that make the ocean so complex. So, yes, there's water in the ocean. It moves on the surface in currents. It moves a lot slower underneath the surface in deep water masses, and they're all connected together through this process of Thermohaline circulation. We'll even use a different color for this one. This is a really big topic. Thermohaline circulation. Really cool. Okay, hopefully I've emphasized how important this is. This is a cool video. There's no text here, but it shows the movement and the connectivity of surface and deep currents. Check it out. Now, we can round out this discussion on a more practical application. So, in the shift from our divestment, there's a good word, from fossil fuels moving into the future, we need a very diverse portfolio of energy supplies. And the oceans provide myriad ways. One of them is using these ocean currents to generate power. The model is simple. Ocean water moves through a turbine. The turbine converts mechanical energy into electrical energy, creating electricity, which we use for energy. Now, this is big. This is ugly. It's expensive. It's a hazard to boats. It's a hazard to marine life. Not currently used worldwide, but there are some systems in Florida on the Gulf Stream. And there's a lot of energy in these currents. So trade-offs to any kind of energy generation, but important to know that we can utilize the ocean in a variety of ways to help support our growing population and our growing economy. Now, if we think about the intersection of oceans and climate, intricately, intimately related with each other. Oceans moderate heat. They transport heat. Here we can see currents, warm currents in red, cool currents in blue. The distribution of continental deserts aligns with where ocean gyres bring cool, dry air from the poles. So southwest, that's a desert. Sahara Desert, that's a desert. Atacama, that's a desert. These all align. Now, what we get are cool ocean currents at the coast with cool, dry air. There's a dry climate joining that. And where warm ocean currents meet the coast, we get warm, humid air, giving us humid conditions. So right there, because of ocean circulation patterns, we can start to understand climate variability. Climate is a big, big topic. Now, on the oceans and climate change, if the world gets warmer, as it is trending now, which it does, climate change is a natural process, increased temperatures melt glaciers. There's a big glacier up here on Greenland. If this glacier melts, it inputs fresh water into this warm surface water, changing the temperature. If the temperature changes, it can change the density, upsetting the balance of downwelling of deep water formation here at the Greenland Sea. This would be really bad because the oceans have evolved balanced in harmony with where the continents are now. Now continents move. Plate tectonics is an awesome facet of our planet. We wouldn't be here without plate tectonics or water or our specific place distance away from the sun in the Goldilocks zone. There's a lot of things that went right for you and I to be here. It's truly phenomenal, fascinating. But one of them right now is thermohaline circulation. So while climate change is going to affect a lot of things, temperature, frequency, intensity of storms, one thing to look out for is thermohaline circulation and the disruption of oceanic circulation, which could lead to disrupting marine life, which would be really bad. Again, the fate of our species truly lies in the health of our oceans. So in conclusion, ocean circulation is awesome. It's big, it's varied, it's complex. There's currents on the top of the surface and deep underneath, and they connect globally through this thermohaline circulation. The movement of ocean circulation supports marine life, transports heat, moves nutrients. And if we are to gain an understanding of how our Earth works and how our oceans work, well, we need to know about the circulation of ocean water. So thank you so much for your attention. Thank you so much for your learning. Thank you for your presence. Have a really nice day.